In the AP exam universe, AP Chemistry is considered especially difficult. Chem Advantage is dedicated to help students learn chemistry to master the AP Chemistry exam. Mr. Musculuk is the teacher. This is a video in a series to help with the multiple choice portion of the AP Chemistry exam. The multiple choice section of the written exam is scaled to be 50% of the 100 total points in the exam. The other 50% is based on the FRQs. A student has 90 minutes to complete 60 multiple choice questions. The score is based on the number of correct responses. The performance level expectations of the MC section have not been explicitly published, but this set of percentages are indicative of the AP score a student is likely to get based on the AP percentage correct and are realistic goals. This series of ChemTubes focuses on difficult MC questions that are based on actual released MC questions. I will explain the chemistry behind the questions and also provide tips on dealing with the MC questions. They will help you show your mastery of AP chemistry on the exam.
I'm going to solve and explain this problem in a little bit less than 4 minutes.
Start by reading the problem to yourself. I'll do the same, and you can follow my cursor as I read it. Okay, that's about how long it took me to read it. Now, let me highlight the important stuff because it's going to help you solve the problem. The first thing, besides, of course, the reaction that you see above it, is that here you're given the enthalpy of a reaction. The number is way over here, negative 196 kilojoules. It's an exothermic reaction. Then this is just sort of filler. And here's something else that's very important. The bond enthalpy of the OO bond. When I read this, I know they want to know about bond enthalpy. And this is what they want, the enthalpy of the diatomic oxygen. They want this enthalpy. Now, the single bond is 150 kilojoules per mole. The double bond is going to be more than that. Therefore, we know that A and B are just too small, and that's going to be wrong. So we can get rid of A and B and be pretty certain that at least get a 50-50 chance of the right answer. How are we going to solve for this? Well, we're given a change in enthalpy for the reaction. We're also given the bond energy of oxygen. Now, we've got an equation that's going to help us. Here it is. The equation says the enthalpy of the reaction is going to be equal to the bond energies, we're interested in that, of the reactants minus the bond energy of the product. That's the equation that you really should know. It's the enthalpy of the reaction, which is negative 200 kilojoules, is the sum of the bond energy of the reactants. Well, here's our bonds. We have hydrogen, oxygen, hydrogen, oxygen, hydrogen, oxygen. We have 4 OH bonds. And we also have 2 OO bonds. So we've got those tossed in. Those are the bond energies of the reactants. Now, we need to have the bond energy of the products, which we're going to subtract from this. That's going to be exothermic. That's why it's got the negative. So we're going to need, again, 1, 2, 3, 4 OH bonds that are being made, and also the bond energy of the product, which is why we picked this equation. Before we put some numbers in this, 4 OHs and 4 OHs. So therefore, they're going to cancel out, and that's going to make things easy. And our equation now becomes this, our 2 oxygen single bonds minus our 1 oxygen double bond. And we've got the numbers for that. We've got the 200 kilojoules for the reaction. We've got the 150 for the oxygen-oxygen bond, which we have highlighted. And then subtracting from that, we've got our double bond oxygen. Easy calculation. And we've got our answer already. Very, very, very good. Let's look at the actual explanation behind all of this. And this equation, the idea is that if you take your reactants and their bonds and break them all apart, that's endothermic. If you broke this, all of them, it would take a certain amount of energy. In fact, I looked up the OH bond enthalpy here, and it was 460 kilojoules. So if you ripped apart all of these bonds, it would cost you 2,600 kilojoules of energy, endothermic, to put in. But then you'd have a whole bunch of atoms here that you could reassemble. And when you form bonds, important idea, that's exothermic. And when you form then this new bond, this one, and then the double bond oxygen, you'll find that the actual total enthalpy that's released is 2,800 kilojoules. That, of course, included that 460 kilojoules that we made for each one of these OH bonds. So this is a exothermic reaction, and as they said, negative 196 kilojoules. Decomposing hydrogen peroxide is a beautiful reaction. I've got a video here that shows a classic demonstration. Sometimes it's called genie in a bottle, because you use a catalyst, in this case manganese dioxide, and dump it into some concentrated hydrogen peroxide, and you'll see this steam formed. So let's watch the video. After all this work, we deserve a treat.